or to the cloud? I don't know. Okay, let's hope it's recording all right. So, welcome to the social meetings. No. No, welcome to the seminar. So it's a pleasure for me to introduce Jorge Rodriguez. Jorge Rodriguez, is someone who's been with IFISC for quite a long time. He studied physics in Valencia. Then he did the masters here, the IFISC masters, and the PhD under the supervision of Victor Aguiluz. And I worked a little bit also with him. He has worked a lot on mobility in the ocean, of animals and of vessels. He's a pioneer, I think, in this kind of complex systems studies of the movement of marine megafauna with the and has used the largest data sets of this kind. Then after the PhD, he moved to Torino, to the ISI, where he was caught in the pandemics. And later he was for a brief period of time at BIFI doing epidemics in Zaragoza. From there, he got Juan de la Cierva and was doing more on animal movement at the Medea. And then he got the Vicens Moot here, and he's now here a postdoc, although he already has a position in the Spanish National Weather Agency. But until that position is filled, will have the pleasure of having him here. So as I said, he's worked a lot on mobility, on animal mobility in the ocean, mostly on epidemics and the interplays of movement and epidemics. And his work is characterized by using lots of data, but not forgetting about modeling. And so the floor is yours.
Thank you, Juan, for the introduction. Today, I'm going to talk about fishing. I would like to start sharing with you a story about overexploitation. Here, you can see the time series showing the landings of Atlantic cod in the east coast of Newfoundland in Canada. And you can see how from the middle of 19th century, the landings were growing little by little. There was some improvements on the fish that was caught by the fishermen. There is some noise. Every year there may be better years, worse years, but it's growing slowly. But then there were major advances in the techniques that the fishermen were using for practicing these activities. And then there was a sudden growth in the captures of these species. Regrettably, this growth was followed by a large decrease because they were fishing at a rate much faster than what the fishes were able to recover. So then in 1 year, they could not reproduce enough to keep the biomass constant. So then there was a very, very big drop. Then, of course, the government of Canada had to take some action on this. So they took some action, and the first thing that they decided is their exclusive economic zone, the zone where they can manage their resources and where they could guarantee that their fishermen were fishing and not the foreign fishermen. There was 3 nautical miles from the shore, but they decided to extend it to 200 nautical miles. This is in 1976. And this is 6 years before the United Nations decided to keep this limit of 200 nautical miles for all the nations. So when this happened, you can see that there was a recovery. Of course, there were less foreigner fishing fleets in this zone. But the problem is that the space that was left by these foreign fleets was occupied by the Canadian fleets. They were able, with these advancements that were growing and growing, to fish in larger areas, even fishing in deeper depths. So then what happened is that there was another decrease, a total collapse of the ecosystem, not only due to the fishing of the Atlantic cod, but also due to the accidental fishing of some prey of this species. So then in 1992, the government of Canada had to take further action, and they declared a moratoria on fishing. So temporarily, they were banning fishing of this species in the area. But even though this was not too effective because the ecosystem had already collapsed. With this example that I have just shown you, we have seen that overfishing can be a big problem. It's more or less a known problem for all of us. In fact, it has arrived to Netflix. This is a documentary that I recommend you to watch. It's called Seaspiracy. And it's interesting because it can give you a general view of the things that are happening in the oceans. But I warn you, I recommend you to watch it critically, because some of the conclusions of this documentary are not very well supported by the scientific community. So then it's interesting to have a general overview, but we should take care with what we are watching in this documentary. And then, well, we know that overfishing is a problem, but overfishing is the only problem of fishing? Let's see. I'm going to give you 3 examples of things that are happening in the oceans that are related to fishing. First of all, we know that the oceans are helping us fighting global warming. Why? Because the oceans have the capacity of dissolve some of the CO2 that is in the atmosphere. And then this CO2 can be stored as carbon sediments in the grounds of the oceans. Here, for example, you can see an illustration of the amounts of CO2 that are stored in the sediments, in the marine sediments. But what's the problem? The problem is that we have trawling fishing. And trawling fishing is moving the grounds of these oceans, generating some turbulence around there, and then facilitating that the CO2 that is stored in these reservoirs, in these sediments, is released to the ocean, and then it's decreasing the capacity of the oceans for dissolving the CO2. Another problem is bycatch. I already mentioned it a few slides ago. Bycatch, for example, is a very important problem for sharks. And well, everyone is afraid of sharks. They are the bad guys in the oceans. But from ecology, we know that the sharks are very important for the oceans because they are predators that help keep healthy the ecosystems. The problem is that the sharks are caught accidentally when the fishing vessels are doing their jobs in the oceans. And in fact, well, this is something that is causing problems to the sharks because it can cause the death. And even if it doesn't cause the death, it can cause some injuries and some stress in these animals. In this map, well, this map comes from a massive quantification of the overlap between sharks and fishing vessels. And you can see basically the lighter colors in the map indicate the regions where if you find a shark moving through there, it's very likely that at the same time and at the same moment, you find a vessel around. But that doesn't mean that the sharks are caught by the vessels. The sharks could be happily moving around there, and maybe they are not caught by the vessels. However, what we see here is these blue dots, that these blue dots represent evidences of tracked sharks that were captured by vessels. Let me give you the third example. So entanglement with fishing gear. You have here one vessel that is fishing, the nets maybe are not in the best state. So some of them are released from the vessel and they go to the ocean. And accidentally, they can capture some animals. Some animals that are captured, they cause the death in those animals, then the animals are sinking, and then they find some scavengers in the ocean bottom. These scavengers try to exceed the dead animals, then they cut the nets, the net is free again, and they make a ghost fishing cycle. Everything looks a little bit bad, no? So we have overfishing, and we have these three consequences of fishing. But what is being done? What is being done to prevent these problems? Well, let me show you this map. One of the very effective measurements that are taken for preventing the consequences of fishing is the marine protected areas. The marine protected areas that globally you can see here represented as in blue. And also the management in the oceans, as I told you before, is managed through the exclusive economic zones that are the zones that are within 200 nautical miles of the shore. Every nation has the right to manage these exclusive economic zones. And you can see that if just 8% of the ocean is protected by marine protected areas, most of it is within the exclusive economic zones. There are just very few spots where we have marine protected areas out of the exclusive economic zones. For example, here in the proximity of Antarctica, and this large marine protected area in the Northern Atlantic. But in the remaining, in the common resources, what we know as high seas, the areas of international jurisdiction, just 1% is covered by marine protected area. These common resources, where the regulation is, if not absent, very, very weak, we have very, very few places that are protected. In this talk, especially in the first part, what I want to do is to analyze what is happening in these high seas. In these large regions of the ocean that are unprotected. And there could be two hypotheses. One, we could think, okay, so the high seas are farther from the shore, so then maybe nothing is happening there, because maybe for a fishing company, it's better to remain fishing within the shore because they don't have to spend so much fuel to go to the high seas. Or maybe they could think, okay, so I could remain within the shore, but I can go to the high seas, because in high seas I will not have anyone telling me what I have to do. So this is what we are going to analyze in this talk. And how we are going to do this? With data. Maybe you know this page, that this is a screenshot that I took a couple of days ago from marine traffic. So this is this is like the flight radar, the flight radar. So this is for aircrafts, and this one is for marine vessels. And this is a system, automatic identification system, that is tracking the vessels. Basically, it was originally designed for safety, to avoid the collision between different vessels, and it tracks their location. So this data is not freely available. You have to purchase to have access to it, and it's really, really expensive. But well, we were lucky to have access to it. And here you can see, well, different vessel kinds. For example, for me, it was interesting, this route. That is the pink ones are the pleasure crafts from Panama Canal going to the South Pacific and to Oceania. But also you can see in green the cargo vessels, in red the tanker vessels, and for example these ones that are in orange are fishing vessels. So you can this system is classifying the vessels according to their kind. And then what did we have? So well, we were having AIS data exclusively for fishing vessels. The rest of categories were not in our data set. in 2014. And later at the end of the seminar, I will tell you something about other categories in 2020, an interesting year, 2021 and 2022. Our data set is composed of 250 million of locations corresponding to 112,000 vessels located all around the world. And here I can show you an example of the data that we have. An example that is available here. You have plenty of data that you can freely download in this web page, and you can play with it a little bit. And let me tell you a little bit what this data includes. So we select one vessel. This is the identifier of the vessel, but you cannot re-identify it because we were anonymizing the numbers that we are using. And then we have some information like the latitude, the longitude, and this a specific time, and the speed of the vessel in knots. The speed is automatically notified by the system. Later, we will do something else with the speed. So how does this data look? Well, let me show you a movie around Balearic Islands, some days at the beginning of 2014. And you can see here the almost periodic trajectories. For example, if we focus in the port of Palma, you can see that there are some trips every day where they go, they fish somewhere, and then they return to the port. There are some transits, but most of it is periodic movement.
Is there a beam inside for the vessel?
Yeah. It's from I don't remember exactly, but from a certain site, it's compulsory to wear this, to bring this device. And then for smaller vessels, it's optional. So then we wanted to start characterizing what is happening in the high seas. And we wanted to start by measuring what is called fishing effort. Fishing effort is defined as the time that one vessel has spent fishing. And the experts in fisheries always agree that this is highly correlated with the load that was captured. So then we want to characterize this fishing effort, but we have several problems. First of all, a fishing vessel is not continuously fishing. It's not all the time fishing. We can remember from the previous slide, they make a trip, they stand somewhere for a while fishing, and then they return. So then we needed to remove this trip. And in fact, if we look at the speeds reported by the system, we were finding a bimodal distribution. Bimodal distribution, including one mode of slow speed and another mode of high speed. So we were associating these two modes to transit for the high speed and to fishing for the low speed. And then we chose this minimum of 5 knots as a threshold to decide when the vessel was fishing or not. But once we know if the vessel is fishing or not, we have another problem. Another problem is that our data set is discrete. We have discrete location data. We don't have the real trajectory of a fishing vessel so that we can say, okay, this fishing vessel has been spending 5 hours fishing in this region. We don't have this information. And if we have uniform sampling, we could infer it. Because if we have 1 point every minute, 1 point means 1 minute. Okay, no problem. But the problem is that first, the AIS has a different sampling rate depending on where you are. And then other things were happening that I will tell you in the second part of the seminar. One problem, one solution. So we developed a method in which we were discretizing the world in cells of size 0.5 degrees times 0.5 degrees. And then, of course, this is the real trajectory of the vessel, but we never have this. We have some discrete points. For example, this point at T1, this point at T2. And if we have 2 points that are in no-transit mode, that means that they are fishing, then we can calculate the time difference between both. Okay, and then if this time difference was less than 1 day, and the distance between both points was less than 2,000 kilometers, and believe me, maybe 2,000 kilometers looks very big, but this happens in the data, then we consider that they form part of the same trajectory, and we were assigning half of the time difference to the first cell and half of the time difference to the second cell. What we obtained? So this is our global map of fishing effort, where we have some enclosed areas that include the top 10% cells in the world with the highest fishing effort. And our approach was working quite well. We were comparing with other approaches by other groups using neural networks, and the correlation coefficient was quite good. Sometimes this is a lesson that sometimes before starting using modern technologies and artificial intelligence and pollute very much by spending plenty of time training the algorithms, maybe it's not bad to look at the distributions. And then for us was interesting to find some places that are strategically located where there is a very high concentration of fishing effort. For example, in the coast of Peru, close to the exclusive economic zone, here we have many cells with very high fishing effort. In the coast of Argentina and the Falkland or Malvinas Island, I don't want to make anyone angry, we have some fishing effort there. And then we have South Africa with some accumulation of fishing effort, and also in Japan we have some accumulation of fishing. And in fact, if we can quantify the fishing effort that we observe in the high seas as a function of the distance to the shore, we find that most of it is close to the exclusive economic zones. 47% of all the fishing effort in the high seas was in a narrow strip of just 200 kilometers next to the exclusive economic zone. This is a problem. This is a problem because imagine that I'm the politician managing this exclusive economic zone. And I can have the idea of, okay, I'm going to manage these resources in a sustainable way. No problem. But the fish here don't know about the artificial borders. The fish don't know about these 200 nautical miles. So they will be around there, and other actors will come and will get the benefit of my efforts in sustainably regulating this effort. Let me show you an example of this behavior, free riding behavior. Basically, they are, yes?
Maybe why don't you have data in the exclusive economic zone?
Our idea was to characterize only what happens in the high seas. Because in the exclusive economic zones, is everyone manages and up to you. If you want to fish whatever you want, then in 10 years you will not have fish. But in the high seas, it's common resources. So then it's a problem.
But do you know if it's much lower? Like, is there a conflict between the exclusive economic zones and high seas?
It depends. It depends on the nation. If the nation wants to invest on sustainably regulating, then there will be much less. But maybe there's a point when they decide, okay, let's go fish in here like there's no tomorrow. Then, so yeah, this was happening here, and I wanted to share with you an example of what was happening, of the possible consequences of this behavior, where we have some people that are going on the high seas and doing whatever they want. This is Somalia. Now here we have also a fishing effort in the shore. And well, there is some fishing effort on the shore, but within the exclusive economic zone, there's almost nothing. But if you go to the border of the exclusive economic zone, you have plenty of fishing effort. And in Somalia, there used to be many fishermen that were traditionally fishing in their shores. But the problem is that there are here some actors that are removing resources from them. So you have one ingredient, lack of resources. You have another ingredient, availability of weapons to the war in Somalia. This is the consequence. So what can we do? What can we do with the data to help learning about a little bit about this phenomena, about how can we fight it? Well, use network science. So first of all, we wanted to know the structure of fish in the high seas. So we were following the vessel's trajectories, and we were connecting consecutively visited cells, considering cells that are in the high seas and also considering the ports. Then, following these connections, we were applying community detection, and we were finding some structure. Some structure that it was composed of 14 marine provinces. Here you have with different colors. In black is we are showing the trajectories of the fishing vessels, and the colors are showing the different marine provinces that we found in the high seas. What's the problem? That if you look at these black lines, that are the current areas of management in the seas, the FAO zones, the Food and Agriculture Organization zones, they don't have too much to agree with the fishing vessels defined communities. So then what we propose first is that we should be really well informed with the trajectory information from the fishing vessels to decide which are the management areas. And then we propose these 14 provinces as good candidates for being the management areas. But we could go a step further and know who is involved in fishing, who is supporting fishing. And then what we did is check the visits to the ports. Maybe the fishing vessels were not landing in the ports and releasing all their captures. Maybe the customers were not these ports, but for sure these ports were supporting the activity of these fishing vessels. So what we did is between two ports, there was some fishing effort. Then we assigned this fishing effort to the first port visited before that and to the last port visiting after that, okay? And this was the port effort. Then, of course, what we can do is connect the ports to the provinces where we were observing fishing. And we extracted the top 10 ports with the highest fishing effort. Here you can see represented these top 10 ports where you can find Puerto del Callao, for example, another very well known for Spanish people, Las Palmas and Marin Vigo, but you can find also Montevideo, Stanley in Falkland, Malvinas Islands. And you can see also them represented in this map with the bars proportional to the fishing effort in each of the provinces where they were supporting these vessels. What you can see is basically a big level of specialization in the network. Except for the Central Pacific, most of ports were focusing just on one province. And then in Central Pacific, there was much more structure around here. So the ports could focus in different provinces. And also in Indonesia, they were splitting between these two provinces. But once we know what is happening at the port level, in one port, you cannot do too much. You cannot regulate too much. So what we did is aggregating the ports to nations. And then we found this network connecting the countries to the different fishing areas. Here you have the top 20 countries involved on fishing in high seas. Spain is the winner. For me, it's not something to be proud of, but Spain is the winner. And but there is some hope. There is some hope because in these top 10 countries, you find many in the south, many low and middle income countries. And this is an opportunity for me to control and manage. Maybe rich nations should put some benefits, some subsidies to these nations such that they help controlling and managing the fishing in the high seas. One option is to use game theory. I'm a little bit tired of prisoner dilemma. It's a very abstract problem. It's very useful to know the mechanisms. But in this case, we could use game theory to know how much money we should put to convince actors to cooperate. Because of course, if I am cooperating to regulate the fishing in the high seas, but my neighbor is not cooperating, he's going to get all the benefits of fishing in the high seas. So then I propose to use game theory to solve these complex problems. We have a complex network, we have many actors, and then we have a complex problem. And I told you that, well, we would do something else with the data because the data in general was a very good quality data. But there were some things, especially in the sampling rate, that we didn't like too much. Let me show you some information. We were looking at the interevent statistics between two consecutive points. We were looking at the time difference between these 2 points and at the speed. Just this is computed. This is not reported by the system. We compute the distance traveled divided by the interevent time, and then we compute this. So these are the marginal distributions. We see that it decays slowly for the delta t. And also we have the marginal distribution for the speeds, where you can find some speeds that are really, really high and unfeasible. For example, 10 to the 3 kilometers per hour for a fishing vessel. So here you can see the joint distribution of both represented as a heat map. You can see that most of the points fall within here. Remember, we were having high speed mode, low speed mode, but we also see things that we cannot explain too much. And then what we did is, okay, so there are many combinations here, but let's just focus on one case. That is, let's check what is happening when there is a long gap without data. Suddenly, one vessel is in the middle of the ocean, and it stops having data for more than 24 hours. We were calling these silence anomalies, and we found 770,000 silence anomalies out of 250 million locations. This is, for me, it was a very high number. So the first hypothesis that we were having is maybe the devices are failing. No, we cannot blame anyone for suddenly the device that you are carrying starts failing. So we wanted to filter these cases and discard the cases that could be explained by a failure of the device. But I remind you, our data has just latitude, longitude, time, and speed. So it doesn't have anything saying if the device was working well or not, or what was happening before. So what we needed is a method. And our method is very simple, just 3 steps. What we want to do is keep anomalies that cannot be explained by a random failure. So first of all, we consider only trajectories with anomalies, because the others, if they don't have anomalies, we don't have anything to filter. Consider again cells of 0.5 degrees times 0.5 degrees size, and we discarded the cells with a port, according to the world port index. And this is because, of course, I could expect that there are gaps in the data when the boats arrive to the port, because maybe they have holidays, or maybe there are several days that they are not working, so then they arrive to port, they stop the tracking of the device, and then after several days, they start again going to the seas. So that's why we were discarding the cells in the port. And then what we were doing is, we were taking our anomalies, and we were redistributing them randomly in the trajectory, just taking into account that the probability of an anomaly in a cell was proportional to the number of locations. If I have many locations in a cell and I have a random failure of the system, it's more likely to have an anomaly there than if the cell is very seldom visited. So then we did this in its trajectory for each vessel, and we did 10 to the 3 realizations. And then simply in one realization, if the number of anomalies was higher in the random case than in the observed case, we could understand that all the observed anomalies could be explained by the random model. So then we were increasing the p-value. So this is a method just to assign for each vessel and each grid cell a p-value, saying that, and the p-value, a low p-value would mean here that the anomalies observed in that grid cell cannot be explained due to a random failure. Okay, so then we could filter. We could filter the anomalies that were in our data set. So we were selecting in each trajectory the cells with p lower than 0.01. And we found a total of 169,000 remaining anomalies. This is how it looks. Basically, we can see some anomalies again in Peru, plenty of in Europe, in China, also in Japan here, and close to the limit of the Russian exclusive economic zone. But also, this is just the number of anomalies that we were finding in every grid cell. But we were also finding something very interesting. That is, when the vessels that were having some anomalies visited some specific grid cells, they always, or most of times, have an anomaly there. So this was the fraction of anomalies. We computed this as the number of anomalies that we find in a grid cell divided by the number of visits to that grid cell. And in some cases, for example, here you can see in Europe, but also here in the East Asian coast, you can find very big numbers. Most of times when a vessel was arriving to these locations, it was disappearing. And then, well, I don't want to give too many interpretations of this, but think bad and you will be right. So we were characterizing a little bit these anomalies. First of all, with the distance to the shore, most of them were happening close to the shore, but we see that they were decreasing as we are approaching the border of the exclusive economic zone, and suddenly there is an increase. We have an interpretation for what is happening close to the shore, because these anomalies were happening for small vessels. For small vessels that are more likely to be doing traditional fishing. And this is something known that the fishers want to hide their position. Because of course, if I arrive to a place where there are plenty of fish, my competitors also can see that I am there, and they are going to come and start fishing there as well. So then I hide my position, and then others will not know where I'm fishing. So this is something intentionally done for by the fishermen, and typically located close to the shore. And this is something that is happening here. You can see plenty of anomalies. Every red dot is an anomaly, and you can see plenty of them typically associated with small vessels. But this thing was done by big vessels, and then our idea is that this could be big vessels that are approaching an exclusive economic zone where they shouldn't be, and suddenly they disappear. This reminds me a little bit the movies, no? When the bad guys in a movie are escaping from the police by car at night, they go into the forest and then they turn off the lights, no? So the idea is something similar here. They are going to do something that is not totally right, then they disable the tracking system. And we could see more things. So we could represent in color in these maps the number of anomalies. As a fraction of these circles, the fraction of anomalies that were found in these grid cells, we were finding many anomalies. And for example, you can see many anomalies accumulated, not only in the exclusive economic zone, but next to a marine protected area. In the border of marine protected area, they were arriving and disappearing. Also here, there are many marine protected areas. They were arriving, disappearing. Here we have Greece and Libya. This is an exclusive economic zone that is in conflict. And there are not too many anomalies, but every time a vessel was arriving there, it was disappearing. And also you have some anomalies here in the border of the Russian exclusive economic zone. And also here, most of times when a vessel was arriving here, you have an anomaly. This is a conflict zone between North Korea, South Korea, and Japan. So this is something that makes us think very much of what is happening there. But we could also learn more things about these anomalies. So we were connecting them, like we were connecting the fishing effort, we were connecting the anomalies to the ports. We're finding a hierarchy of ports. Most of them are Chinese, but you can find also, for example, Ancona in Italy, Ferrol and Ribadeo San Ciprián in Spain, Valletta in Ireland, Basto in Italy, Harlingen in Netherlands. You could also group them by countries. The winner in this case is China, by an order of magnitude with respect to Spain. And then also you could connect the ports, the port country, with the exclusive economic zone. But we have a problem, because if we say that the vessels are staying out of the exclusive economic zone and they are making the anomaly there, then we are never going to detect them inside the exclusive economic zone, because they are always going to stay in the border. So what we did is extending the exclusive economic zones, and every point that was in the high seas was assigned to the closest exclusive economic zone. And we can see here a complex structure. For example, interesting links, China and Argentina. But also we can see that many European countries are connected between themselves, United Kingdom, with France, also with themselves, United Kingdom, but also with their neighbors, with Ireland. Spain also plays a great role, making this network a little bit complex. So this is the part of the analysis of anomalies. Then we don't have too much time, but I wanted to share you another piece of work. That is, well, we were getting access to a very, very, very nice data set, something that is very well done by Hub Ocean. Hub Ocean is a Norwegian non-profit foundation. They are developing now a platform with plenty of data for the ocean. And I was lucky to have access to one private preview week where I could access all the data that they have in the ocean, including the AIS data. And well, so within 1 week, I had to do all the work, but it was challenging, and it was nice also to play with platforms, because everything was computing online. I didn't have to download anything. So I was having some software there. I was launching the software and getting the output. So we wanted to characterize shipping in the Arctic. I think that this is a very timely topic, because you know that the ice is declining in the Arctic, and it's opening the opportunity to have new routes. In one hand, is something negative, because it's a very fragile ecosystem, and then it can get pollution, it can get acoustic impacts, and even collision with the vessels for the animals living there. So it's an ecosystem that we should protect. But in the other hand, this can help reducing the CO2 emissions by making shorter commercial routes. So this is the map of how it was looking. These 3 years, 2020, 2021, 2022. We were representing the shipping density. So basically, how many hours of transit were detected in every square kilometer in the Arctic. You can see two routes, basically the route of the Northwest Passage and the Northeast route. And well, something very interesting for complex systems, no? So we represented the distribution of this shipping density. We found a power law with an exponent 1.78. And this could think, okay, so this could maybe mechanism underlying this phenomenon, but we don't know too many mechanisms of in complex systems, no, to regenerate problem laws. Basically, the main one that we know is the multiplicative noise, and get richer. So then we were proposing some models. So we were proposing null models of traffic density. First of all, 1D transit. So basically, you have one destination that is at x equal 1. And then you have several origins for the transit that are randomly distributed between 0 and 1. And then you compute the distribution of the density that you observe according to this model in 1D. You can do the same in 2D. So in 2D, you can put all your vessels in the origin. You can put the destinations at x equal 1. And then every vessel catches one destination and goes from the origin to the destination, moving with a constant speed and in a straight line. Okay? So basically what this is leading is to a dilution of the density, because here you have many vessels per area, and here you have few. You can do the same if you change the symmetry of the system, and instead of having one Cartesian coordinates, you have polar coordinates, and you put your origin at 0, 0, and your destinations, you distribute them in a circle. And then my question is, how is the density distribution in both cases? And so, do you have any bet, any guess? So, well, this is the answer. For 1D, we have a uniform distribution. I think that this is not too much surprise. So it will be a power law with exponency, still a power law. And for 2D, we have a real power law with an exponent -3. And this was suggesting us that the traffic that we were observing in the Arctic with this exponent 1.70 something is between both, between 1D and 2D. So the vessels typically are following straight lines, but sometimes they do other things. And in fact, we could check this with different vessel categories that were leading to different exponents. So for example, passengers that are more directed, they go very clearly from one place to another, had lower exponents. And fishing, which is more something sparse because the fishing vessels are moving, looking for the fishing grounds, were leading to higher exponents. Let me give you some conclusions of this talk. First of all, we saw that in globally connected ecosystems, especially the oceans, what happens at the high seas, this free riding, does not stay at the high seas. We saw also that game theory can be useful to solve less abstract, to solve real problems. And the question is, how can we convince actors to cooperate for sustainability? We also saw that we can learn from missing or wrong data, illustrating suspicious behavior. And also we saw a new mechanism that is just spatial density patterns from transit flows leading to power law distributions. My final thought is that part of this data that I used was purchased. So my final thought is when we are going to have open data for sustainability research. Thank you.
No, thank you, Jorge. And now I think you had a surprise for us.
Yeah. So yesterday, when I was preparing the seminar, I was thinking a little bit. I saw plenty of green. Most of us have some T-shirt, some caps from IFISC with the green. And then I was thinking, which should be the IFISC fruit, no? So then I brought some apples, and you can pick some apples when we are done.
Okay, thank you. So, any questions to the speaker?
Parliamo Cirillo. Oh, okay. Okay.
And no more questions? Really? No?
And thank you very much for the talk. It was really interesting. So my question is there any information about the fishing methods these vessels are using? Because I could think about there could be some differences between like using large nets or picking fishes one by one, if this affects the fishing effort on different areas. I'm also thinking about the differences in catching, because some people or some cultures like take a lot of fish, they let it suffocate. Another cultures like Japan, where there is a lot of fishing, they kill the fish one by one to preserve the meat and to kill the meat in a humane way. So my question is there any data, or you have any guess on if the fishing method affects somehow the results?
Yeah. I was mentioning the neural networks that were using and were used for obtaining the fishing effort. They are also used to classify the fishing gears that every vessel is using, and there are some the training data set for these neural networks is contrasted database showing that every vessel has a special technique. So this information, is available.
But anyway, there was like a very high correlation between both, so it seems like it's not very important for the conclusion, your conclusions.
Yeah, no, but it's important when you go to, for example, you want to analyze bycatch, then it depends on the technique that you are using. Some species will be caught or not. So then you need to narrow down your approach and just select some vessel categories specifically for some species.
Okay, thank you very much.
No, it was just simple. Just making numbers. You find 169,000 anomalies up to 200 million. So I would say naively, this is not very large. I would expect many more. So only less than 1 per 1,000. So is that only 1 out of 1,000 ship make this anomaly?
No, this is
Otherwise,
let's come back to it.
you have
Yeah.
done that.
This one, no?
Yeah, 169,000
Yeah.
out of 250 million
Points,
points.
not
Yeah.
vessels. Points.
So these are numbers.
But you have a point every minute. So typically what you will have is good trajectories. If you are carrying the device, you know that you are carrying the device, and then you should have a good, a nice trajectory on there. But just some of them do this.
The question is how many of them? I didn't get that. How many vessels are involved in anomalies?
I don't remember the number.
It's not one every 1 out of 1,000? You have so many points, and so many points are.
Typically, many anomalies were occurring for a specific vessel. So they have this strategy and they do it many times.
Points is the location. The vessel makes more points. So that depends on the number of vessels.
Yeah, I think that even if one vessel is making many anomalies, you have some path between the port and the place that they are making the anomalies. And the anomaly is just one because you stop and then you just have one anomaly. But between the port and the fishing ground, you have several hours with plenty of points.
I mean, that already answered the question, but I have another one. So you said that you will have another position.
Yeah.
Like, will you do something similar there, or yeah, what are your ideas for the future?
Well, first of all, I don't know what will be my specific role there. I would like to bring ideas to to bring ideas in data analysis, in visualization, but also to learn many things there. And I think that they have very, very, very good data sets on meteorological observations, and some of them could be applied also to the ocean analysis. So then one of the big limitations that we have is data available, and the data is there, but generally either it's not available or it's hidden. So then having these large data sets available, it's very good.
So if there are no more questions, let's thank the speaker again.